What's up, peoples? This video is intended to help you with multi-part dynamics problems, basically two problems in one. We've done this in the past. This video has to do with coefficient of friction as well. But basically, you can read the problem and you realize that something's starting from rest, it's being pushed, so it's increasing its speed, then the push is no longer applied, and it slows to a stop. So this is a speed up, slow down problem, if you will, with forces involved. Another big thing is, hey, after this, so that's telling you there's a whole new type of motion. All right, and it's basically two dynamics problems in one, which involves an FBD, forces X, forces Y, and kinematics. Now, if you'd like, you can set up both parts, like an FBD, forces X, forces Y, kinematics, part one, part two, FBD, and keep going. I don't have enough room on the screen to do that, and I tend not to do that, actually, for some reason. But if you do part one and you set it up and there is not enough information to solve for what you need in part one, then focus on the slowing down part and keep going. Some people quit after part one. We're like, well, yeah, there was nothing to solve for. Right, and it's a two-part problem. So move on to part two and see what you can do. So let's get after this. I'm going to start with the usual, which is an FBD. Truth be told, it's the second time I'm doing this video because I forgot that this was below the horizontal, and I went pretty far into the video and screwed it up because, oh well. So, take two. 15 degrees. We've got a normal force because it's sitting on the surface. We've got the force of gravity because, hey, Earth's around saying, hey, I'm attracted to you. That's the dumbest thing I've said in a long time. And we have the force of friction opposing the motion. All right, we're going to go after the forces in the X that cause the mass to accelerate in the X-axis. Looking at my free body diagram, we have 500 newtons to the right at an angle of 15 degrees. We've got friction, which we're going to replace with mu Fn right away. The mu that we're going to use, the coefficient we are going to use is the kinetic. Both are given, but it does say it's sliding. This thing is definitely not static or stuck to the surface or anything like that. So it's mu Fn, which causes the 40 kilogram mass to accelerate. Now, some of you are getting good at this, and you might be starting with the forces in the y-axis, hoping to get the normal force so you can immediately sub it in here. That's great. I love it. Do that. If you don't feel comfortable doing that, then don't. Then just follow a procedure. It'll all work out. We're going to sum the forces in the y that cause the mass to accelerate in the y. Luckily, this thing is not accelerating in the vertical axis. If it left the surface, there would be no friction, right? So we've got the normal force acting up. We have 500 newtons acting down at an angle of 15 degrees. And we've got gravity acting down. And would you look at that? We can get the normal force. Isn't that amazing? Equals 0 newtons. So we get a normal force of 521 newtons, which I can then take and sub in here, and I'm not going to rewrite it for time's sake, and get that the acceleration in the x-axis, a little high here, but it's 8.17 meters per second squared. Wow, somebody's pushing really hard. Not all problems are realistic. All right, well, I can keep going. I've done the forces X, forces Y, I've done a free body diagram. I can now perhaps, maybe do a little kinematics. Let's get after that. So if I do kinematics, I've got initial velocity of 0. Final velocity, I don't know. Acceleration, we just got. It's 8.17 meters per second squared. I don't know the distance, and I do know the time is 4 seconds. By now, you should know that the key to a multi-part problem is that the final velocity of part 1 is equal to the initial velocity of part 2. And vice versa, if you're working backwards through a problem. In this case, we can work forward because it worked out that way. So I'm going to use math step number 2. That's final velocity equals initial velocity, which happens to be 0, plus acceleration times time. And I get that the final velocity is the acceleration times time. And the final velocity is, I wrote it down, I swear, is 32.7 meters per second. I'm wondering how many of you find these videos annoying. Anyway, I also need to get the distance traveled because this problem's asking for total distance. So I'm going to choose math step 3. You could use number 4 if you'd like, but I like this one because you know what? It says delta D equals, and the initial velocity is 0, which makes life easier. So 1/2 acceleration times time squared. And we get the distance for part 1 is equal to 1/2 acceleration, which is 8.17 meters per second squared, times 4 seconds squared, giving us a distance for part 1 of 65.4 meters. All right. I mean, that in and of itself is one problem. Well, now we go on to part 2. This is when it's skidding to a stop. So I'm scrolling down here. All right. Part 2 is skidding to a stop. And I just realized it's going to bother me. And this will not be edited, so you will suffer through this. That I didn't write, like, part 1 here. It's kind of bothering me. All right, I'm satisfied now. And I'm sorry you had a, like, interlude there. All right, part 2, we're skidding to a stop. We've got a normal force. We've got gravity. And we've got friction bringing it to a stop. Okay. I will do the sum of the forces in the x, because that's where I tend to start. But some of you are like, why don't you start with the sum of the forces in the y and get the normal right away? All right, tough guy or girl or whatever, you do that. So we have negative mu times the normal, that's our friction force, causing the 40 kilogram mass to accelerate. Oh, we don't know the normal force, and you did suggest that I should go over here and do the sum of the forces in the y first, but I didn't listen to you. This thing is not accelerating vertically up off the ground or down through it, so we only have that the normal force is equal to mg, or minus 40 kilograms times 9.8 meters per second squared is 392 newtons, which I can then sub in here. I would like to bring something else up here, because some of you may be aware of this, but 0.3 times 392 newtons causes this mass to accelerate, and we get a horizontal acceleration as it slows of negative 2.94 meters per second squared. Okay, side note, this is a standard skid problem. Skidding looks like this. Okay, it's that simple. We only have the normal, gravity, and friction. And some of you may remember a shortcut, not really a shortcut, but just a fact that when it's only normal, gravity, and friction, the mass divides out. And I could prove it to you by solving for Fn here as Fn minus mg equals 0. Ooh, I don't like the way I wrote that. This is not going to be edited. I'm so sorry. This should be equal to 0, and then I should have written Fn equals, what did I say? 392 newtons. I'm sorry about that. So Fn minus mg equals 0, or Fn equals mg. If I then sub that in up here, I get 0.3 mg, negative, don't forget that, Josh, equals ma. And the mass, since it's in every term, will divide out, and I still get the same answer. So some of you may know that already, that the mass divides out. Good for you. That's nice. And our last step here, because we're asked for total distance, is to use kinematics. So we have the initial velocity. The final velocity, I believe it skids to a stop. Acceleration, which we just got, was negative 2.94 meters per second squared. Delta D for part 2, I don't know. Delta T, I don't know. The initial velocity, I know. It is the final velocity from the previous part. What a surprise. And if I'm looking for distance in part 2, I'm looking at math rep number 4, so I'm going to do this for you pretty quickly. It's the final velocity squared, which is 0, equals the initial velocity squared plus twice the acceleration times distance. So we have 0 equals 32.7 meters per second, quantity squared, plus twice the acceleration times the distance for part 2, which we don't know, and we get delta D for part 2 is about 182 meters. How do we get delta D total? If you don't know this, we need to talk, like seriously at this point. We should be talking. I'm running out of space here. Oh yeah, very much so. And to get delta D total, it's the sum of the distances, which I didn't write out in the beginning, but you can do if you think it might be helpful. So we have a distance for part 1 of 65.4 meters plus 182 meters equals a total of roughly 240 7 meters. And that's about it. That was a very long problem. But it's basically 2 problems in one, and the key is that the final velocity from part 1 is the initial for part 2, or vice versa, and the sum of the distances or sum of the times equals the total distance or total time, respectively. All right, let's sum this puppy up for you. All right, we have general problem solving strategy. It is a 2-part problem, so you're going to be doing FBD, forces X, forces Y, kinematics for each part. And it is worth writing, although I neglected to do so, that the distance of part 1 and 2 added together are the total, and the times for part 1 and 2 added together are the total. This can be useful. Like maybe you're given the total distance and you know the distance in part 2 and you're looking for something in part 1. Well, the key to getting it is to use this to get the distance in part 1, so you could do kinematics or whatever. So it's probably worth writing down. The final velocity of part 1 is equal to the initial of part 2, and vice versa, hence the red arrow going back and forth. That's the connection. So if part 1 doesn't get you what you want, move on to part 2, because then maybe you can get the initial velocity of part 2 and work backwards through the problem. But if you're organized and not panic, let the work do it for you. Don't try to do it all in your head. And if you're given both coefficients, choose the appropriate one, either skidding, rolling, sliding, or stationary, or stuck, those kind of things. But stay organized. Set up as much as possible and plan a course of action. Like, again, if you don't see enough in part 1, move on to part 2. And big hint, if you're asked for the acceleration in part 1 of this problem, or the force applied in part 1, odds are you could set up part 1. You're not going to get very far. You got to go to part 2, get information so you can work backwards to part 1. Oh, I wasn't even looking at the blue here, and I'm just talking. And look at that. That's exactly what I just said. Man, I am amazing. And because of that, I'm going to give this video 3 out of 5 stars. Wouldn't change a thing at all.